let us take a quick example and see how to use the limit laws in a particular situation. Okay, for example, we'll say that f of x is 4x squared plus 3x minus 1. We want to know the limit. Find the limit of f of x as x approaches, it doesn't matter too much, we'll just say 1. All right, so if that's the case, that should be the same as the limit of the rule for the function, replacing the function symbol as x approaches 1. But according to the sum difference rule we have here, right, I have a limit applied to a sum or difference. That becomes the sum or difference of the two limits, or more. It's not restricted to 2, that's just the way the rule is stated. So therefore down here, I should be able to distribute, in a sense, the limit operation to the 4x squared, distribute the limit operation to the 3x, and distribute the limit operation to the 1. There. Okay. Moving further, I've got a product of functions now. All right, so up here very quickly, I've got 4 times x squared. I've got 3 times x. So therefore, the limit of a product of two functions, yes, this one's constant. Yes, the 4 is a constant function and 3 is a constant function, should be the product of the two limits separately. But we know that the limit of a constant, right, if the first function here is played by 4 or played by 3 respectively, then we know from further back here the limit of a constant is that same value. Okay. So we should now have that the limit of 4x squared is the same as the limit of 4 as x approaches 1 times the limit of x squared as x approaches 1. And then so too for 3x. You should have the limit of 3 as x approaches 1 times the limit of x as x approaches 1. And finally you have minus the limit as x approaches 1 of the constant function 1. Okay, so we're getting close to the end of this now. You can see it's still rather cumbersome. More efficient than using the definition on this thing, for sure. Nevertheless, still a little bit bothersome in terms of efficiency, but getting better. All right, we know that the limit of a constant is itself, so this should now be 4 times what? Times, we know that the limit can move inside an exponent. We saw that here, right? The limit can move inside and apply itself to the function within the exponent, and that function is just the x function, the identity function x. So we should have limit of x as x approaches 1, and whatever that is, big mystery, we'll square it. And then a limit of 3 is of course 3 itself, regardless of what x is approaching, doesn't matter because that's a constant. And we still have a limit as x approaches 1 of x. And we know this is minus 1. Again, limit of a constant is itself, regardless of what x is approaching. So the only thing we have left now are these two limits, and they're both just the function x. And we know that we mentioned back here, the limit of x as x approaches a, whatever a is going to be a, of course, because as x approaches a, x approaches a. What else is it going to be? So that's what we apply down here. And so we conclude we have 4 times 1 squared, right? Because x is approaching 1. It says right there underneath it. Plus 3 times 1 minus 1 equals, well, I guess that's 6. So there's our answer. Limit of this function as x approaches 1 is 6. Now, something more important going on here. And it is, let us now look, what would have happened if we had just simply plugged in 1 for x in the first place? Right? If we evaluated not a limit, but just the function value itself. Evaluate f of 1. Okay? What would we have gotten? It would have looked like 4 times 1 squared plus 3 times 1 minus 1. Well, lo and behold, it would look exactly like our last line. No different whatsoever, and of course that would be 6. This is an important result. The fact that the limiting value for this function as x approached 1 was 6, which was exactly the same as if we had simply plugged 1 into the function in the first place. Okay? So this is actually true for all polynomials. And not just for polynomials, but also for rational functions where they're defined. And it's even bigger than all that. Really, what's going on here is the limit of f of x as x approaches a will be f of a. Right? The limit of the function will be the same as the function value at a when f of x is continuous at a. So therefore we have a great luxury. We can compute limits very easily, and we're going to call this the substitution rule. All right. This is the substitution rule. As long as we know that our function is continuous at the value a, which x is approaching, we can simply plug in the value of a into the function, and that will be the same as the limit.